Today, we shall begin with the second lecture on the subject of wavelets and multi-rate digital signal processing, in which our objective would be to introduce the Haar multi-resolution analysis, about which we had very briefly talked in the previous lecture. Before I go on to the analytical and mathematical details of the Haar multi-resolution analysis, or MRA as it is called for short, let me once again review the idea behind the Haar form of analysis of functions. Recall that Haar was a mathematician or mathematician scientist, if you would like to call him that. And the very radical idea that he gave was that one could think of continuous functions in terms of discontinuous ones, and do so to the limit of reaching any degree of continuity that you desire. What I mean is, start from a very discontinuous function and then make it smoother and smoother, all the while adding discontinuous functions until you go arbitrarily close to the continuous function that you are trying to approximate. This is the central idea in the Haar way of representing functions. We also briefly discussed why this was something important. It seemed like something silly to do at first glance, but actually is very important. And the reason why it is important, as we mentioned, was if you think about digitally communicating, say for example, an audio piece, you are doing exactly that. The beautiful smooth audio pattern is being converted into a highly discontinuous stream of bits. What I mean by discontinuous is, when you transmit that stream of bits on a communication channel, you are in fact introducing discontinuities every time a bit changes. So, after every bit interval, there is a change of waveform, and therefore, discontinuity at some level, even if not in the function, in its derivative or in its second derivative, whatever be. Whatever it is, the idea of representing continuous functions in terms of discontinuous ones has its place in practical communication, and therefore, what Haar did was something very useful to us today. What we are going to do today is to build up the idea of wavelets, in fact, more specifically what are called dyadic wavelets, starting from the Haar wavelet. And to do that, let us first consider how we represent a picture on a screen, and I am going to show that schematically in the drawing here. So, you see, let us assume that this is the picture boundary. And I am trying to represent this picture on a screen, whatever that picture might be. So, just for the sake of drawing, let me draw some kind of a pattern there. Let us say you have a tree and some person standing there. I mean, forgive my drawing, but whatever it is, and some grass maybe here. Now, this is inherently a continuous picture. How do I represent it on the computer? I divide this entire area into very small sub areas. So, I visualize this being divided into tiny, what are called picture elements or pixels. So, each small area here is a pixel. A picture element, so to speak. And there are, for example, suppose I make 512 divisions on the vertical and 512 divisions on the horizontal, I say that I have a 512 cross 512 image, that many pixels, and in each pixel region I represent the image by a constant. So, the first thing to understand is there is a piecewise constant representation. Let us write that down. There is a piecewise constant representation of the image. One constant for each piece. And that piece is the pixel or the picture element. Now, suppose I increase the resolution. So, I go from a resolution of 512. So, I take the same, what I mean is I take the same picture, In this case, I make a division 512 cross 512. In this case, I make a division 1024 cross 1024. Now, obviously, the pixel area here, let us say the pixel area here is P 2 and the pixel area here is P 1. It is very easy to see that P 2 is 1/4 of P 1, and therefore, I have reduced the area by a factor of 4. Naturally, if I use a constant to represent the value or the the intensity of the picture on each pixel here and do the same here, what you see in this picture is going to be closer to the original picture in some sense than what you see here. So, in other words, we can capture this by saying the smaller the pixel area, the larger the resolution. Now, this is the beginning of the Haar multi-resolution analysis. The more we reduce the pixel area, the closer we are going to go to the original image. Even though this captures the idea that we are trying to build, it is not quite the idea of the Haar MRA. The Haar MRA does something deeper, and that is what I am now going to explain mathematically in some depth. Now, here I gave the example of a two-dimensional situation, which apparently is more difficult than one-dimensional, but it is easier for us to understand physically. We can more easily relate to the idea of a piecewise constant representation in the context of images or pictures, but the same thing could be true of audio, for example. So, you could visualize a situation, though seemingly more unnatural, where you record an audio piece by dividing the time over which the audio is recorded into small segments. Now, let me show that pictorially, it would be easier to understand. So, suppose for example, you had this waveform here. So, the one dimensional version. So, suppose I have this is the time axis. and I have this waveform here. Assume that this is the audio waveform, audio voltage recording. Let us, without any loss of generality, assume that this is the 0 point in time. So, let time be represented by t, and let this be the 0 point in time. Now, let me assume that I divide this time axis into small intervals of size t here. So, this point is t, this point is 2t, and so on. And I make a piecewise constant approximation. That means, I represent the audio voltage in each of these regions of size t by one number. Now, what is the most obvious number, or what are the set of most obvious numbers that one can use to represent this waveform in each of these time intervals? For example, in this time interval, or for that matter in any of the time intervals, it makes sense to take the area under the curve and divide by the time interval to get the average of the waveform in that time interval, and use that as the number to represent the function. So, here for example, you can visualize that the average will lie somewhere here. I am just showing it in dotted. So, average. So, intuitively it makes sense to represent the voltage waveform in each of these intervals of size t by the average of that waveform in that interval. Is that right? Let us write that down mathematically. So, what we are saying, if you have a function x of time, a good piecewise constant representation is the following. Over the interval of t, over the interval from say 0 to t, now strictly it is the open interval between 0 and t, the representation would be integrate x of t dt from 0 to t and divide by t, the average. Now, of course, on any particular interval of t the same holds. So, we say that on every interval of t, on any particular interval of t, of size t, the average would be obtained by 1 by t integral over that interval of t. When you write it like this, you mean that particular interval of t. Integral of x t with respect to small t. This is a piecewise constant representation of the function on that interval of size t. Now, the same thing could be done for an interval of size t by 2. So, over an interval of size t by 2, you would similarly have one by t by 2 integral over that interval of length t by 2 x t dt. Now, we are going closer to the idea of wavelets. Let us pick a particular interval of size t. In fact, again without any loss of generality, let us choose the interval from 0 to t and divide it into two subintervals of size t by 2. So, what I mean is, take this interval of size t 0 to t, I am expanding it. So, you have this function here over that interval. Divide this into two subintervals of size t by 2. First, take the piecewise constant approximation on the entire interval of t, and I will show that by a dot and dash line. You can visualize the average would be somewhere here. So, this is the average on the entire interval 0 to t. Now, I take the subintervals of size t by 2. So, I have this subinterval of size t by 2. I use a dash and cross to write down the average there. So, I have dash and cross here. You can visualize that in this subinterval the average would be somewhere here, and similarly in this subinterval you could write down an average something like this. Now, let us give this a name. Let us call this average A on t. Let us call this average A1 on t by 2, and let us call this average A2 on an interval of size t by 2, and let us write down the expressions for each of these averages. What are the expressions? A t is obviously 1 by t integral x of t dt from 0 to t. A1 t by 2 is 1 by t by 2 integral from 0 to t by 2 x t dt. And similarly, A2 t by 2 is 1 by t by 2 integral from t by 2 to t x t dt. For convenience, let me flash all the three expressions before you once again. A t is the average over the entire interval of t, A1 t by 2 the average over the first interval of t by 2 with this expression, and A2 t by 2 the average from t by 2 to t the second subinterval of size t by 2 with this expression. And just to get our idea straight, here again is the picture. Now, the key idea in the Haar multi-resolution analysis is to try and relate these three terms. So, to relate A t, A1 t by 2 and A2 t by 2, and it is in that relationship that the Haar wavelet is hidden. So, what is the relationship? Now, the relationship is very simple. I mean, all that we need to do is to notice that we have divided the integral from 0 to t into two integrals over 0 to t by 2 and t by 2 to t, and then remember there is a slight difference in the constants associated. So, we have a constant of 1 by t in A t and a constant of 1 by t by 2 in A1 t by 2 and in A2 t by 2, whereupon we have this very simple relationship between the three quantities. A t is half, I leave it to you to verify, it is half of A1 t by 2 plus A2 t by 2. do we interpret this? Let me try and kind of focus just on this relationship. In other words, let us just focus on these three constants and make a drawing there. So, what we are saying is something like this. I have this a t there. I have this a 1 t by 2 here, and I have this a 2 t by 2 there, and we are saying this plus this by 2 gives you this. In other words, this is as much higher above a t as this is lower. What we are saying is these two heights are the same. That is what this relationship implies. Now, another way of saying it is, if I were to make a piecewise constant approximation on intervals of size t, how would they look? So, let me just sketch them. So, I take this function once again here. I have this function here. I have divided it to sizes of intervals of size t. Let me show just two intervals for the moment. So, this is how the function would look when you make a piecewise constant approximation on intervals of size t. And when you do it on intervals of size t by 2, it would look like this. Something like this. Now, this is a function. So, let me highlight it. Now, let me darken it. This is in its own right a function, a piecewise constant function, the one which I have darkened here. And this is in its own right, the darkened part is in its own right an approximation to the original function here. Similarly, let me now darken this and put some other mark on it. Let us keep the crosses. So, I will darken this, but I will put crosses on it. So, this is also another function. So, dark and cross function is another function. That is in its own right an approximation too. So, let us give them names. Let us call this function, just the dark one, as f1t, and let us call this function, the one which we have shown with dark and cross, as f2t. f2t minus f1t is like additional information. What we are saying is, instead of a piecewise constant approximation on an interval of size t, when we try and make a piecewise constant approximation on intervals of size t by 2, we are bringing in something more. Go back to the original case of the picture, we have inherently underlying a continuous two-dimensional picture, a continuous two-dimensional scene. When we make an approximation with a 512 cross 512 resolution, then we have actually brought in one level of detail. When we go to a 1024 cross 1024 representation, the level of detail is 4 times more. What is the additional detail that we have got in going from 512 cross 512 to 1024 cross 1024? In effect, when we take this difference f 2 t minus f 1 t, we are answering that question.